We start? I think
yeah, you can start.
Okay, so before the seminar, I want to make an announcement that I think we already did, but I still want to mention that we have a YouTube channel for our Crunch seminar, and we're putting every week's recordings on the YouTube channel. So feel free to check it out. You can search Crunch Group in the YouTube website or app, and it shows the channel. And yeah, please subscribe. And yeah, okay, so hello everyone, welcome to this week's Crunch seminar. Our first talk is given by Oded Ovadia from Tel Aviv University, Israel. Oded is a PhD student in applied mathematics. He went to college at 12 and obtained his bachelor and master degrees at the age of 17. His field of study is application of deep learning to PDEs and numerical methods, and he currently also works as a data scientist at Microsoft. There's a fun fact: Oded works in the same lab as our colleague Adar used to do at Tel Aviv University. He is currently sitting at the chair Adar used to sit, using the computer Adar used to use. Okay, so without further ado, welcome Oded. You may want to start the presentation.
Yeah, thank you very much for the kind introduction and also for the invitation. It's really great to be here. And it's also really great to see some familiar faces. I've had the opportunity to visit Brown a couple of months ago, and ever since I've joined a bit of a collaboration with some of your team members in the area of Hebbian or biologically plausible learning. So some background about today's talk. During my visit to Brown, I actually participated in a meeting with Professor Panagiotis and also Dr. Dima Krodov from IBM, where Dima mentioned a paper he co-wrote with some authors titled "Can a Fruit Fly Learn Word Embeddings?" And during that conversation, Professor Panagiotis kindly suggested that I could present this paper to you in your seminar. And obviously, I'm really excited because this is a really fun paper, and I hope you'll enjoy it too. Just to make something clear, this is a paper review. I did not participate in the writing of this paper. This is not my work, and all credits go to these people over here, who are the authors of this work. And you can see it was a sort of a joint collaboration between different research institutions, including IBM, MIT, and others.
Oded, let me add here that Leopold Grimberg was a PhD in the Crunch group, and
really?
I was his advisor. Yeah, he
he
now moved to AMD, but he was at IBM until recently. Yeah.
Oh, I see. So that's our agenda for today. We'll start with an introduction about biologically plausible learning, about word embeddings. We'll describe what word embeddings are, and we'll talk a bit about the fruit fly brain and understand how it works. And then we'll move on to the learning algorithm, which is the main, is the crux of the matter of the paper. Then I'll show you some results taken from the paper itself. And finally, I'll show you a fun little experiment about Cranch-specific results. So for the introduction, what's our motivation? Word embeddings. Generally speaking, computers don't know what words are. That's obvious. Computers work with numbers. So we need to find some way to convert words into numbers. So one of the most classical methods to do it is using a bag of words, which is a sort of a one-hot encoding, but this results in a very high dimensionality and not a very smart representation of words. And word embeddings are a way to do it in a low-dimensional way, and perhaps even getting more interesting representation of words. So let's look at an example. Let's take the sentence, word embeddings are interesting. If we take a bag of words approach, we'll have to one-hot encode everything. So, okay, we have a word, we have 1 and zeros, we have embedding are interesting. That's very clear. But then if we move on, we have a lot of columns. So if we have a vocabulary of, say, 1 million words, we would need 1 million columns in order to actually represent it, which is a very poor representation. But then embeddings offer us a better alternative. What if instead of taking 1 million columns, we just take a vector of size, say, 400, and try to represent each word by a representation of the vector itself. So that's very much in a nutshell what embeddings are in the field of NLP, natural language processing. And currently embeddings are basically state of the art. Like most algorithms that deal with NLP use some sort of embedding. And perhaps the most famous example is BERT, which came out in, I think, 2018, like 4 years ago. And it's one of the most cited papers in the history of deep learning. with around 50,000 citations. And one of the problems is that it's a very big model with 335 million parameters. So we ask a question, could nature offer us a better biological alternative? So what is biologically inspired learning in general? The main idea is to try and replicate nature and the brain, because currently the way neural network operates is very much different from how the human brain or any brain operates, right? Just because it says neuron doesn't mean it acts like a real neuron. And the idea of biologically inspired learning is to learn the synaptic connections between neurons in a better way. So first of all, it is a binary way, just like in the brain. Neurons are either on or off. And as a result, it's supposed to be way lighter and more efficient. And finally, with the addition of neuromorphic computing, which is binary in its essence, maybe we could really speed up things in that domain. Why fruit flies? This is not the first animal that comes to mind when we talk about someone brilliant. So we know that they have rather simple brains, but surprisingly, they're simple yet somewhat complex compared to other animals. I mean, they're not humans, obviously, but they're not jellyfish too. They're somewhere in the middle, and as a result, a lot of neuroscientists have managed to get a really good grasp of how the fruit fly brain operates. So it has around 25,000 neurons with 20 million synapses, and just for the sake of comparison, the human brain has somewhere between 80 billion and 100 billion neurons, with more than a quadrillion, which is a million times a billion synapses. And the mushroom body is a major area of the fruit fly brain that is responsible for processing sensory information. And I know multimodality is all the rage right now in deep learning. We see all sorts of models that combines different modalities. Well, the fruit fly brain does it without any sort of algorithm. We get an olfaction or sense of smell sensors. We get a thermohydrosensory system, which can grasp the temperature or humidity, and also vision inputs. And this is the main schematic view that is going to be with us until the rest of the talk today. We have as inputs the projection neurons, or the PN, which are the three modalities I mentioned earlier. And then we have the true heart of the mushroom body, which is the canyon cells. And one can think of the canyon cells as basically a hidden layer, right, with neurons. So we get projection neurons as an input to the canyon cells. And then we have the anterior third lateral neuron, or the APL. And as you can see, we have a sort of a recurrent connection between these two layers, where the job of the APL is to suppress most neurons. So if we have, for example, the fruit fly brain around 2,000 cases, the APL could leave only 2 or 3 on while turning the rest off. And here's a simulation of the fruit fly brain, courtesy of the folks at Janela and Google. And you can see different parts of the brain here in the 3D simulation. This is the olfactory part of the sense of smell. Here's the visual part. Now for a high-level view. Here, you can say it's perhaps, at least for me, it's way more complex than what I imagined a fruit fly would be. So there is something to learn from it. And the attributes of the mushroom body, first of all, that it has synaptic connections. So there's at least something we can learn. There's a recurrent network we mentioned, but also very important mechanism is the winner takes all, which is also existent in the human brain, where the vast majority of neurons are turned off. So that's one of the things that make it so efficient, that if we have 2,000 neurons, only 2 or 3 are actually stay on. And finally, there is one very important mechanism, which is a clustering mechanism. If a fruit fly smells a bird or a cat, its output, its brain's output, should be very similar. It's danger, because both are predators of the fruit fly. So we expect that inputs that yield similar results should have similar representations. And this is how it relates to NLP and embedding. This is basically a type of embedding. We take a series of inputs and try to embed them into a different representation. This time, this representation centers around concepts such as danger or food or any other evolutionary mechanic. And the idea is that we can try and find some similarity metrics between the representations. Let's talk about the learning algorithm itself. So first of all, we have to encode the data, right? If we have a corpus of words or tokens, this is the NLP term, we need to find some way to convert it to numbers. So here we have, for example, the sentence apple stock rises. And if we take stock to be the target word or the central word of the sentence, then its context should be apple and rises. And we can encode it very simply, just sort of a one-hot encoding. And notice that there is no order here, right? Apple was before rises, but since this is just a one-hot, we have rises and apple. And here in the target vector, we have the actual target we're trying to predict. So that's a way to turn the problem of finding word embedding from something that is completely unsupervised to something that is supervised. We can get a context and we can get a target and find a mapping between them. Here is a more mathematical formulation. Let's say we have a training corpus of n voc, where voc stands for vocabulary. So we have n voc different words. And we can split the data into odd n-grams. N-grams are a combination of words, just like we saw with apple stock rises. In this case, n is 3, because it's 3 words. And the reason we need to take odd n-grams is just so we could take the central one as the target. And then if we look at some n-gram A, we can generate a training vector, VA, with components binary, right? This is just what we saw in the previous slide. Notice that the size of this vector is 2 times n voc, because from 1 to n voc, we have the context, and then the rest is just the target itself. But then we're talking about some form of machine learning problem. So we need a bit more of a statistical approach. We need to define a probability of words. And that's very easy to do. We can think of a probability over a given corpus, just as the frequency of the word, right? We take the number of occurrences and we divide by the size of the entire corpus. And here the notation they used in their paper included a modulo over n voc, but basically just the same thing, because we can think about the context vector and the target vectors as 2 representations of the same probability distribution. So they have exactly the same distribution over each cell. So now we have we take the binary vector we had, and we can use an element-wise vector division by the probability. I know it's not very common to see this notation, but in this case, it's well defined because of the way we define the probability distribution. It's over the corpus. So each word already appears in the corpus, otherwise it wouldn't be part of the vocabulary. So in that case, we have no zeros, and it's okay to divide by 0. And we take VA divided by P as the main input of the model. That's how a single sample looks. Here's the learning problem itself. Remember, I said that we'd see the schematic view a lot in this talk. This is the second time already. And now, instead of just taking the connections of the synapses for granted, we can think of it as a W, as a matrix of synaptic connections with K neurons, right? So we have here the connections, K times 2n voc, right? Because we have 2n voc inputs as each vector and K neurons over here. And now the main idea is to try and learn this W, which is a fully connected network. So usually we just use a stochastic gradient descent, choose some backside, choose a number of epochs, take the derivatives of the loss function, and so on, train a neural network. But in this case, we're interested in a biologically plausible neural network. So we can do this. So this is not a regular SGD, not regular weights. We need to define the equivalent of a loss function, which in this case is an energy function, which we want to minimize. And this is the main definition of the energy function. I know the notations are not yet defined. We'll define them in the next slides. But just from looking at it, we can see a few things. First of all, we have an iteration over all data points, right? And also we have some inner product, which can be thought of as some similarity matrix and a normalization factor. Let's define everything. Denote by mu the indices of the projection neurons, N, and I the indices of the canyon cells, or KC. So we can view W, the matrix of weights, as either columns, W mu, or element wise with W mu I. And then for each engram we have in the dataset A, we can iterate over all columns, all mu's, and calculate the similarity matrix between W mu and VA. And finally, we take a mu hat to be the maximal index. So we can think of it like this. We have a lot of columns, and we take the column that is the most similar to the given engram. And the inner product in this case is just the element-wise product, which is pretty similar to the cosine similarity. Why specifically this choice of energy function? Let's think of some intuition behind it. Consider the case of a uniform distribution of the worlds, or PJ, just 1 over n VOC. All worlds have exactly the same probability of appearing in the corpus. And then if we take a look at the definition of the energy function, we can just take P out because it's constant. So we have minus constant times this expression over here. So once again, for each A in the data set, or for each sample VA, we look for the closest column. So this could be thought of as a variation on a spherical K-means algorithm. Actually, in the case of uniform distribution, this is exactly spherical K-means. If we think of this as a form of a cosine similarity. So we iterate over all samples and find the closest column. Obviously, this is not actually spherical K-means because we have, the factor here P, which is in most cases not uniform. So we have to take the probability distribution into account. Now, this is the main part of the algorithm. This is truly the core of all the Hebbian learning and biologically plausible neural network. As we said, our goal is to try and replace SGD. So in order to do it, we need to define some sort of learning rule. And if you go into the literature and look for Hebbian learning or biologically plausible learning, you'd see that most learning rules look something like this. This is not unique on its own. They're all variations of very similar learning rules. But let's still try and examine and see what we see over here. So we have epsilon, which is the learning rule. Sorry, on the left-hand side, we have the delta W mu I, which is how we update. This is one step of the update of the weights. So we have a learning rate. Inside over here, we can see we have the actual inputs themselves. And it's interesting to note that we divide by the probability. And since probabilities are between 0 and 1, I remind you that it means that very rare words would actually get higher weights. And very common words would get lower weights within the algorithm. And for those of you who are familiar with NLP, this is very similar to what happens in algorithms such as the TF-IDF. And then what we have here is just the product of the weights. And finally, some form of an activation function. You notice that the probability is not inside the activation function. The authors of the paper tried adding it into the activations and using the activation without it, and found empirically that it performed better without the probability. And this is the definition of the activation function. Just for the function G, we take all of the inner products, and we get 1 if this is indeed the maximally driven neuron, or in the words we said earlier, the closest column, it's 1. Otherwise, it's just 0. And why do we do that? Well, we said that we want a sort of a winner-takes-all approach, right? So we just take the maximally driven neuron each time for the activation. And now for biohashing. Now that we have an algorithm to learn the weights, how do we represent the inputs? How do you find the embeddings? So denote K, uppercase K, as the number of KC neurons, and lowercase k as the hash length, or the cutoff parameter. And just for the sake of simplicity and an example to keep in mind, Let's think that uppercase K is 2000 and lowercase k is 50. So what do? We want to generate for each sample VA a binary hash code HA of size uppercase K. So we go over here, we iterate over all columns from mu equals 1 to uppercase K. And then for each column, we compute its inner product with VA. And once we do that, we can find the top lowercase k values. So if we have 2000 values, we can just take the top 50 ones, the largest ones, and say, all right, the columns that are corresponding to these ones are 1, and all the rest of the columns are just zeros. So we get a sort of sparse encoding with only 50 ones, and the rest are zeros. What's the intuition behind this biohashing mechanism? First of all, it mimics what we said about the APL, right? The winner takes all. It isn't really recurrent, unlike how the APL works, but it does suppress most of the neurons. It leaves only a few values of 1. And just in terms of notation, if we think in a biological perspective, the inner product here, W mu times VA, is basically an electrical current in the brain.
Excuse me, can I ask a quick question?
Yeah, sure.
Hi, this is Panagiotis from Pacific Northwest National Lab. So you said about the winner-takes-all approach, but the way you explained it initially was that this winner-takes-all happens between the KC and the APL. But now I see an extra layer of winner-takes-all between the PN and the KC.
Yes, that's true. There are two mechanisms.
Right. So they're both aspects of the same winner-takes-all approach, or is it that here in this algorithm, this extra layer of winner-takes-all is in addition to what happens in the fruit fly mechanism?
Yeah, thanks for the question. Actually, I noticed that too when I read the paper. They didn't really explain the minutiae of how the fruit fly brain acts. So I don't know to answer from a biological point of view if the fruit fly brain has two different winner-takes-all mechanisms, but that's what they use in the algorithm. You're right about that.
Okay. All right. Thank you.
Thanks. So let's talk about some results from the paper itself. We need to discuss first which applications we have in the case of machine learning. So one example would be static word embeddings. We take just a single word and find its embedding. Another, perhaps more interesting and more relevant to real life aspect would be the context-dependent word embedding, where we get a sentence with a context and we would like to find the embedding there and see whether the same words in different contexts would have different meanings. Another example is word clustering. We just try to find similar words. And another is document classification, which is pretty self-explanatory. You get documents of different kinds. You would like to classify them correctly. And the training set the authors of this paper used was the Open Web Text corpus, which is the corpus of unstructured text. And it's a very large data set. It has around 32 gigabytes. And think about how large that is. I mean, it's easy to get to 32 gigabytes when you're dealing with images, but with text, it's pretty hard. And you can see that the vocabulary size is 6 billion, which is huge. And the evaluation metrics that the authors use are pretty common in the field of NLP and the semantic analysis. First of all, the cosine similarity, which I briefly mentioned earlier. And equivalently, there is the Spearman's rank correlation, which instead of a dot product, we have a covariance. Instead of the vectors themselves, there is some sort of ranking. And there is also a division by a standard deviation instead of the regular normalization. But for all intents and purposes, these metrics could be somewhat equivalent. And in the case of their work, they actually used data sets that had human annotated scores. So it was very easy to calculate metrics. Here's an example. In the case of static word embedding, they took 6 data sets and tried to find how close the results of their embeddings were close to what a human said, right? So if we take the word cat and dog and try to find out how similar they are, a human would say a certain number, and how close is that number in the terms of the Flyvec algorithm. And you can see over here, this is a pretty surprising result, right? We expected to see something good, but all of a sudden we see that the Delphos turned it ours, this is the Flyvec, actually does not operate as well as the other word embeddings, which they use the glove and the Word2Vec and the state-of-the-art, which is in most cases just BERT. And all three are types of word embeddings. So what happens here? Why is the Flyvec algorithm not as good as the rest? The reason is because this is an unfair comparison. We take a binary algorithm and compare it to a continuous algorithm. Algorithms such as BERT can yield vectors of floats of continuous numbers. And the fruit fly, due to the hashing mechanism we mentioned, only yields binary vectors. And the claim of the authors in their paper is that continuously trained embeddings may actually result in richer representations of words because there are more degrees of freedom to the vector. But their other claim is that consequently, because binary is only 1 bit and the float is either 32 or 64 bits, their embedding actually requires only 3% of the memory compared to the continuous one. So
how about the cost? Do they mention the cost for training?
The energy.
Yeah, energy. Yeah, cost. But yeah, memory is one thing, but actually the operations. Yeah, computational complexity.
It's very efficient. It's very efficient. I actually tested it myself and saw that it was very efficient.
Okay, so they sacrifice accuracy, but they're much faster, right?
Yes, especially if you compare it to, say, BERT with 335 million parameters that takes a whole farm of GPUs and weeks to train. Yes.
How about Word2Vec? How about Word2Vec? How is it? How much faster is Word2Vec? Is basically a graph. So how much faster is compared to Word2Vec?
I didn't see if they had a comparison of it, but Word2Vec is pretty old by now. So
yeah. No 2Vec maybe, no 2Vec.
I'm not sure because I don't know how long it takes to train a Word2Vec or its variants.
Okay.
Right. And over here you can see this time a third approach of a binarized approach, where they take 3 different embeddings. In this case, you can see the slashes over here. They took a pre-trained version of glove, a pre-trained version of Word2Vec, and they retrained glove on a specific data set they used for their case. And then for each of these 3 cases, they used a different binarization technique. Now, explaining these techniques is beyond the scope of their paper and obviously beyond the scope of this talk, but I could just mention very briefly that they combine, for example, a sign-based approach, and they combine an iterative approach, a spectral approach. You can see PCA, they do PCA, and then hashing, all sorts of different approaches to take a continuous vector, a continuous embedding such as glove, and turn it into something that is binary. And this case, the results are much better than the previous cases, right? We can see that in 2 out of 6 data sets, Flyvec actually achieves better results than all its 15 methods, right? And even in the first case, they get a result that is the second best. So it's pretty competitive. And now to the task of the context-dependent word embeddings. And before we get onto the numbers themselves, we can see the results of the algorithms. I think it's way more enlightening to see it that way. If we take the sentence design of Apple, latest iPhone, in this case, everything is lowercase. If we were to look just at Apple, we couldn't know if that means Apple, the company. But since we're human beings, we are aware of context. So we know, okay, design and iPhone, this is not the truth. And we can see the 10 nearest neighbors in the hash code space that was produced by Flyvec, design, web, Android, iOS, Apple, Nvidia, all words that are pretty similar to Apple in its tech context. But then when you take the sentence of filling sweet apple pie recipe, the algorithm yields chocolate, sweet, crispy, also for some reason noodles. I don't know if there's addition of noodles and apples, but maybe. Syrup, coconut, cheese, cinnamon, and words that are related to food. And then for another example, we can take money in bank checking account. So obviously this is bank, the financial institution. We get money, credit, loans, and so on and so forth. In the case of the boat on the bank of the river, we get river, lake, mere, island, which shows us that the algorithm is capable of understanding context. And here they compare their algorithm to different state-of-the-art methods. And you can see two different data sets that are context dependent. And this W or omega notation means the size of the window. So omega equals 0 means no context at all, just the board itself. Omega equals 3 means 3 words, and so on. And you can see in the left data set, their algorithm was pretty competitive compared to other algorithms. But in the right-hand side, you can see that it was way better and also almost as good as BERT, only BERT defeated it. And it's interesting to note that in the left-hand side, actually, window size of 0 was the best. And the authors explain it because they looked at the data set, at this data set, and saw that it has a lot of single words without any context. So it makes sense that a smaller window size would be better. If I recall correctly, the number was 86% words without context. But on the right-hand side, they had a data set which had way more context between its words. And we can see that the flyback was very competitive. And I just emphasized, in this case, they compared it to continuous representations. And even in the continuous case, the context-dependent flyback proved to be very good and was able to find very long-term dependencies with a window size of 21. And as for the text of document classification, what they did is they took the text CNN neural network, which is a famous neural network for document classification, and just retrained it with their algorithm operating on the data set. So they embedded the values and then transferred it into the neural network and compared it to glove, to word2vec, to BERT, and another algorithm that is based on the autoencoder. And they found that it was pretty competitive, but not as good as the context we saw earlier. And one other major advantage of this algorithm is its explainability. You can look at the representation and get quite a lot of knowledge for it. So if we take a given query, convert it to a bag of frauds, calculate VA as before, this is the same. And then we can look at the top 4 currents based on the case ignorance. And that's what the authors did over here. And they created a website where you can take a query. So, for example, let's take another Apple example. We have Apple latest iPhone has an improved apps connectivity. And here are the top 4 neurons with the highest activations. And we can see which tokens or which words yielded the highest activations. So we have app, mobile, Windows, Android. So these are words that are related to Apple or to mobile. And here we can see specifically latest, won't, modified, no, system, new, which is perhaps more related to consumerism or consumption of Apple products or advertisement of Apple products. And the interesting part about it is that we can see some sort of a clustering mechanism inside the neuron itself. We can take another example. Stock market plunged on Tuesday following analysis reports. So by far the highest neuron has a value, market, stock, oil, Bitcoin, currency, all sorts of financial words. While the second one has Saturday, night, Friday, morning. This is probably due to Tuesday appearing in the query. So it actually clusters around ideas that are related to parts of days or parts of the week. So that's a very cool aspect of their algorithm. And now let's move on to some crunch-specific results, which I promised earlier. I created a crunch dataset by using the archive API. I took 100 abstracts from papers that were uploaded by you, to archive. And I filtered according to mathematics, physics, and computer science categories. And I ended up with a data set with 140,000 characters and a vocabulary size of 3,000. And the main point of this little exercise was just to try the algorithm for myself. You know, it's one thing to look at the results from the paper. It's quite another to try it and see how it works. And here's a very nice result from the Crunch dataset. This is before the algorithm. I just use a word cloud over all of your abstracts. And you can see over here, you have neural networks, DeepNet, PIN, data, function, PDE, differential equation, basically a summary of all things you do in your group. So I thought it was really fun to see it in such a way. And then for the training, I used the flyback on this data set. I used 400 KC neurons. And Professor Kanedakis, you asked about efficiency. And for this data set, it took me less than a minute to train it on a very simple GPU, where most of the time was actually the pre-processing and not the running of the algorithm itself. It's very efficient. Thankfully, the folks who wrote this paper uploaded a lot of their code to GitHub, so it was very easy to see. The results are embeddings. And then we can take the embeddings and for any given input word during inference, calculate the top 15 most similar words using flyback. Now, obviously, this is a toy example. I use 140,000 characters. They use 6 billion vocabulary size, which means a way larger data set. And still, we can see by using the input word DeepNet, we can see all that looks somewhat related. Time to solution, differentiation, schemes, classical, matrix, function, theorems. And I also find it pretty funny the word black box actually came out. And if we look at another example, we can see the input word of a derivative, where we get the, for example, x for derivative, which makes a lot of sense. F pins, accurately multi-grid equation, words that seem somewhat related to derivative. But then I saw we have the word taxonomy over here, which was very odd because I couldn't think of the way taxonomy is related to derivative. So I went over the text and I find out that taxonomy appears only one time in the entire corpus. If you recall, in the algorithm, we divide by the probability. So because it was such a rare word, its weight was pretty large. And then I looked at the context, and it was actually a paper published by Amea and Professor Kanedakis that says the taxonomy of activation function in the next sentence, it mentioned derivatives. So the only context flyback figured was that taxonomy is related only to derivatives and things that were in the following sentences.
How did you pick up like G pins, which is one paper by the Young guide? I see G pins on the middle right, but not not X pins, for example. Is that because of the author? No. How did G pins end up there? Yeah.
I think I saw X pins. Let me see. Maybe in the word cloud itself. I think X pins appeared in the word cloud, but perhaps it didn't appear close enough in the text to the words derivatives and DeepNet. But I'm pretty sure that it's somewhere in here.
Okay.
Yeah. So finally, let's conclude and talk about some future work that could be used in this domain. We saw that the network of the fruit fly brain can be repurposed for machine learning purposes. We saw that it is useful for NLP purposes. That is very fast and memory efficient. And also, a very important thing, it's actually pretty explainable. So that leaves us with the question whether this framework and this line of thinking can actually be used for PDEs. And I guess that's what we have to study next, right? So thanks, everyone.
Thank you, Oded. This was fascinating. So the next paper will be, can a fruit fly solve a PDE? Solve the Navier-Stokes equations. I think that will attract some attention.
Definitely.
In order to improve its flying.
Do we have any question for our speaker? No. George, I think our second speaker is not here yet. So what do we do?
We'll ask a question. We'll ask Oded questions.
Sure.
Did you get to play with BERT? Because there's a version, a free version. Did you try to run BERT yourself?
Yes, I've done so before, but not relating to this specific exercise. Not on the crunch data set. Running before other data sets, and it's pretty easy because you can get pre-trained weights.
I have a question. So, hi, this is Panos again. So these embeddings, you said that, for example, taxonomy showed up because it was just one time, but it was close to derivative. But these embeddings, can they also look at somehow more non-local effects, like derivative appearing in one paragraph, but then it's somehow related to the context on the next paragraph, not in the next sentence? So, because the reason I'm saying this is you mentioned applications, possible applications to PDEs, and in PDEs you can have these non-local correlations and non-local phenomena, like in elliptic problems where everything is coupled to everything. So if you want to apply these ideas from embeddings, it would help if you know, local, it would help, right? Think of it as having local features in a flow, since George mentioned the fluid flow, but you could have also non-local features. And I'm wondering if these embeddings, I don't know, it's just, you know, thinking out loud. I just heard your talk, so. Yeah,
that's a very good question. And actually in the paper, I just used a very, very simple version of Flyback, but they have shown to use window sizes of 21 to iterate over data sets and just input very long sentences.
Okay.
Right? So, yeah, so in that case, they could find some long-term dependencies.
Okay.
And it's also very interesting, just if we were thinking out loud together, to think how the attention mechanism could be used
yes.
to find out long-term dependencies, because that's how BERT operates. So
yeah, no, that's actually a great alternative to embeddings, right? This attention mechanism, right?
Yes, exactly. And actually, BERT is using attention to compute embeddings.
Yeah. So it would be interesting to see what would be the analog of attention in the Flyback. I mean, I don't know how it works because it also has this winner takes it all, which somehow suppresses a lot of information. But anyway, yeah, no, this is fascinating, especially, you know, the trade-off in accuracy that you get with only 3% of the cost. You get something that could be second best or even best in certain tasks. So that's impressive. Yeah, that's a main claim. Thank you.
Leonard, you have a question?
I don't have any questions, but I did want to say that this is a very interesting talk. I'm one of the things that I do personally find very interesting is like out of the box alternative computing methods and algorithms that are outside the standard framework and also like nature inspired and biology inspired. So I think this is a very interesting direction. Sparse binary encodings is also like much closer to you know, how the brain is hypothesized to work. So it's an interesting direction. I think there's definitely like good future results can come out of this direction.
Oded, maybe you can say a little bit about, because these are people here are pinheads, right? They're not Hebbian learning people. So can you say what Hebbian learning is, and maybe you can talk a little bit about the PNS paper and what you're doing with continuation of Dima's work. So just explain to everyone Hebbian learning and also the computational complexity that involves, so people can appreciate why we're interested in that. Yeah.
Yeah, sure. So Hebbian learning is basically a way to try and mimic the behavior of the brain more faithfully than what currently happens in neural networks. And it's actually a very old concept, even older than neural networks themselves. And it evolved over time, and people tried to find better ways to make algorithms converge. Because the original Heb rule by Heb was actually numerically unstable. So that caused a lot of problems early in the development of Hebbian learning. And ever since, people have been trying to find different learning rules that that could help us learn the weights in a better way. And the idea is, first of all, the human brain. You have something to say?
No, I was just going to say here that our professor in our department, Eli Binstock, is one of the first people in 1984 who corrected the Heb's model with Cooper, who is Nobel laureate in our university. Yeah. Continue, please continue.
Yeah, sure. Thanks. So we know that the human brain, and also apparently the fruit fly brain, is a very efficient machine. And if we look at algorithms such as, let's take DALL-E, for example, where it has to understand a sentence and write a picture, any 3-year-old child could probably do it. You tell him, go paint a house with a balloon in the sun, he could do it. Without using a farm of hundreds of GPUs and training it over a couple of months using millions of dollars of value in electricity. So we know that the human brain is way more efficient than what we currently have in the domain of machine learning and deep learning. So the idea is to try and mimic this efficiency and use it as a mathematical algorithm on the computer. And also with neuromorphic chips that could help compute binary data, this could really speed up computation.
But can you say something? So do we have backpropagation, for example, here?
Here, no backpropagation.
Okay. That's why I want you to zoom in a little bit on the computational complexity. What type of operations is required for what you did, or for the Hebbian learning, the other paper that Dima Krotov produced, the PNS paper? So can you talk about the computational complexity, the type of operations?
Yeah,
maybe
sure.
other can interfere also.
Yeah, I can add a little bit. So Hebbian learning rules are not necessarily connected to the brain. Basically, they are a way to formulate weight updates. We can think about it a general way, or a general set of ways to formulate weight updates using sometimes even just inner products between the weights and the temporal elements and some other things. And they can be used to actually do only forward local learning. And this is what leads to a lot of interest from a lot of researchers, because we don't need backprop. It's very efficient. We can actually formulate our learning using forward gradient, or even not gradients. In our brain, basically, it's assumed that there is some sort of a Hebbian learning rule. Usually, the most famous one is spiking time-dependent plasticity. So going forward in the brain between neurons, what's applied is some sort of a Hebbian learning rule. So what we started doing with Oded, and actually with Qian, based on Dima Krotov's work, is trying to apply these tools or these mechanisms for regression. The natural way to use them is for classification, because with neurons, we can have like one odd vector at the end based on the number of neurons that we're going to use. So everybody's using them for classification, and there have been a lot of new advancements in that field. And for regression, it's a bit more tricky, because like the Hebbian learning rules basically create a representation of the data. How do we create a representation of a, let's say, wave propagation or heat dissipation? Dissipation, yeah. We would like to have a way to represent that using a set of neurons, but this is more tricky than we thought, and this is what we are currently investigating, trying to take a physical process and use Hebbian learning rules to find a more interesting representation for that. And so off topic, something else that I may have wanted to say. So I was talking with Oded throughout the week about this fruit fly, and we were discussing a little bit of other directions about how to do that. And I really kept in mind, how can we use this fruit fly algorithm for functional regression? Because the fruit fly algorithm basically finds connections between the inputs. In this case, it was words, right? So find a word or all the words that are very close to that word in terms of context, not in terms of so with that, we can actually think about kind of symbolic analysis for functions and PDEs, because we do know that there are some PDEs that are very similar to one another by the solution, and we can actually try to think about symbolic analysis for PDEs using this, and maybe like based on we ask for example, for a advection equation, and we get all the equations that are very similar to this one in some sense, and this can have some cool insights. Yeah.
Okay, so but the main point is that we want to abandon backpropagation. Hebbian learning is one way of doing it. There are problems with stability, like you point out. And there are, this also was used in spiking neural networks, but it was abandoned now. There are other ways, but we will pursue Hebbian learning the stable way through Oded.
Yes.
Any other questions? I see Panos is here for the second talk, but thanks very much, Oded. This is great. Let's work on this direction.
Yeah, thank you.
Zogren?
Yeah, we proceed to the second talk. So our second speaker is Dr. Panagiotis Tsoutsanis from Cranfield University, UK. He's currently a senior lecturer in computational engineering sciences, the founder and the head of the Advanced Numerical Methods groups, and the author of the open source CFD software named UCNS3D. So I'll put the link to the website to the chat. Yeah, and Panagiotis' main research fields include numerical methods, computational physics, high performance computing, and turbulence modeling. He has led several developments of numerical frameworks and software algorithms for massively large-scale computations. So without further ado, welcome, Panagiotis, and you may want to start your presentation.
Thank you very much, Glenn and George, for the kind invitation. And yeah, good afternoon to everyone.
Panos, while you are setting up, I want to say that Panos' talk is not on machine learning, but I wanted to invite him because I was very impressed with the framework that we develop. And of course, for our pins, we need a lot of data. We need lots of simulations. So they have a framework that we could be using to generate data, since everything is open source, and a lot of people, including another friend I know, Lim Fu, is involved, I think. But that's just a disclaimer, Panos, so they don't expect you to talk about fruit flies or something else.
Yes, thank you. So today I'm going to talk about a little bit about the UCNS3D software that we have put together with a number of colleagues, and present the philosophy, the history a little bit of the software itself, its current capabilities, and things that we are doing in terms of future developments. So this is the overview of the talk. So we're going to start a little bit with the background, philosophy, how it all started, showcase some of the present capability, and move on to the future developments. So to set the stage, we are encounter three challenges. The first one, in terms of continuum modeling, is that for compressible flows in particular, that we witness flow problems with really rich flow structures, flow physics, that most of the times they have contradicting requirements in terms of numerical methods required. So we have regions with really strong gradients that dictate certain types of numerical methods to accurately resolve them. But we have some delicate flow features present at the same time, which require numerical methods with low dissipation in order to be able to evolve them correctly in time. All this is happening while we have scales of different sizes that, depending on the kind of simulation that we are running, we might want to resolve, or we might not be able to resolve some of them. Moving on to the second challenge that we are facing is that we encounter complicated geometries in realistic applications. So geometries that are not, let's say, simple enough to use a structured grid or a Cartesian mesh because they have complicated features. So unstructured meshes have evolved a lot on this field to be able to accurately represent this kind of complicated geometries, and they are used by industry a lot. And the third challenge is something that it is quite, let's say, not so obvious how to evolve the software in a landscape where the hardware is evolving really fast. So, for example, systems like Aurora or the Summit, where they cost close to $1 billion, they have a short lifespan. And within this lifespan, we have to make sure that our software, our numerical methods are running as fast as possible in these underlying architectures, and making sure that we make the best use of the taxpayers' money by using these systems. So when I started my PhD, these challenges were still there. And the main motivation was, something, there is a gap in the sector in terms of very high order finite volume methods for unstructured meshes. Most of them were up to second order accurate. Some of them were up to third order, but with one mesh type. So the main idea was to develop techniques for very high order for finite volume framework. The reason was more about having existing techniques in finite volume methods that we can easily scale up and apply the methodologies that we're going to develop for turbulent flows and so on. But we were really going after 4 distinct characteristics. So we want a method and a framework that it is really robust. So we have non-oscillatory properties. The second one is that we can achieve high order of accuracy in regions of the flow where we can achieve them. The third one is that it should be computationally efficient, and we should be able to run massive simulations and to be able to demonstrate excellent parallel efficiencies. And the fourth one is that it should be expandable to other systems of equations that we want to evolve later on. So there was a really rich tradition in the department that I was working on in terms of methods developments for compressible flows. And this is one picture from the early 90s with Tito Toro and Phil Rowe back in the day here at Cranfield, where they did really pioneering work in terms of numerical methods development for compressible flows with their approximate Riemann solvers. And then this work ethic and philosophy and track record was passed on, and all the people that got involved later on in the department did significant contributions in compressible flows. Just to name a few, with multiphysics with Romensky, implicit Adler simulation with Dimitris, other with Vladimir, Lomax correction with Ben. So several research work and development was taking place at the department in terms of numerical methods for compressible flows. So it was quite natural for me when I started to building something. And the main framework that we used was the finite volume framework. So we integrate everything within the control volume. We are limited to conforming mesh elements. And the key, let's say, goal is to be able to accurately, not accurately, to be able to have a high order accurate prediction for these terms inside the fluxes, the gradients, so to have a really good approximations for them. And one way that we did that was by performing the well-known reconstruction in finite volume framework, where we have the main constraint being to ensure that we are able to constrain the mean value within every cell. And this mean value, it should be equal to this integrated polynomial within its control volume. The problem with finite volume methods, of course, is that you need to find and obtain the coefficients for these polynomials that we're using, and we're using different types of basis functions. So in order to obtain these coefficients, we have to solve linear systems. And in order to populate these linear systems, we actually build some stencils. So we build some stencils in order to...
Can I ask something?
Yes.
When you say high order, how high is high? Because
we have gone up to, yes, we have gone up to 9th order.
Ninth, okay,
which,
9 is pretty
yes,
high. Yeah.
Which is not that practical for the kind of applications that we're doing. Our typical workhorse is 3rd, 4th, and 5th order methods. Okay. So one of the disadvantages of the classical finite volume methods is that you need to build up really large stencils to solve these linear systems, because you need to find these coefficients by requiring more equations than unknowns. And what we did back then was to transform the stencil, the considered cell here illustrated in red color, and the neighbors from the physical space to the reference space. That was done mainly to reduce scaling effects and to reduce the impact of different element types and different mesh sizes that they're going to have in the reconstruction. Another important parameter was that we used the decomposition. That was eventually a key component in achieving high order of accuracy. And the primary reason for that is that for industrial scale applications, the meshes that we end up working with might not be of really good quality elements throughout the entire computational domain. So this might pose certain, let's say, robustness issues for certain methods. So we decided that we had to decompose every non-tetrahedral or non-triangular element, and we were limited to linear elements throughout this work that we did, because you can easily end up with non-planar faces in meshes of, let's say, full aircraft and so on. So this transformation is used just for building the matrices that we only do it once at the beginning of the simulation, which is actually the matrices, the pseudo-inverse matrices that we use for the least square reconstruction. So we do a least square reconstruction that is solved through a QR algorithm or an SVD. Most of the time we're using least squares for the kind of work that we are doing. And then the first method that we try to implement, that it is both non-oscillatory and high order accurate, is the Wino variant for the finite volume, where we reconstruct entire polynomials to achieve a certain order of accuracy. But instead of combining lower order polynomials to achieve a higher order solution, we didn't use this approach initially. So we used polynomials, the same order of polynomials for every stencil in the domain. Depending on the smoothness of the solution present at each of these stencils, each of these stencils will get a certain weighting factor that in essence is dictating how much of this information is really valuable to us to perform the reconstruction. And the reconstruction was performed either in characteristic, primitive variables, characteristics, conservative, or primitive variables. So this is one of the ways that we use, I think, as many directional stencils as the faces of every element. And it was really expensive. So that was our first approach. And we did some benchmarking with the linear advection equations and Euler equations and parallel implementation when I was doing my PhD. The key target was to ensure that we can achieve the designed order of accuracy for different types of meshes. And the main idea is that we can reduce the CPU time to achieve certain errors with the same computational resources. So that was the main driver for going after a high order finite volume framework. And we also applied it to more complicated problems like supersonic and hypersonic flows within the Euler equations. Of course, the results that you see here are for unique and idealized cases. We are not going to achieve always the designed order of accuracy, because there might be strong gradients which might reduce the order of accuracy close to these strong gradients like shocks and so on to first order or second order. Away from that, then depending on the type and the quality of the mesh, we might be able to achieve a really high order of accuracy. So the WINO methodology is able to blend these things together. So that was our initial, let's say, try. Throughout the years, however, we initially started, I finished it back in 2009, and we started applying these techniques to different set of problems. We did some work on climate modeling with some very well-established test problems. Then we moved on to Navier-Stokes equations with viscosity, looking at turbulent flows without any turbulence models. Then later on, we introduced turbulence models. We did some work on adaptive method refinement. We moved on to multi-physics and rotating flows. So I'm going to present you this journey and how it actually evolved, and in terms of the methods, the models, and the software side of things, because they are all equally important. So we started with trying to look at adaptive mesh partitioning. So we partition the mesh, but depending on the type of method that we're using, we need to perform a different partitioning, because certain elements, element types, or certain areas within our domain are more expensive compared to some others. We also did some work to improve lower order methods. So second, or let's say up to third order methods with a low Mach correction for unstructured meshes, which it was not a straightforward extension from the low Mach correction that was implemented for the structured grids, because different element types like tetrahedrals or triangles, they have really low dissipation characteristics. So they behave different with this low Mach correction if it is directly translated from the structured meshes. Then we did some work with Michael Dumser lately on making central non-oscillatory methods, so combining really compact stencils. So you can see at the top here the directional stencils that we use for, I think this is a fourth or a fifth order method on an unstructured mesh. And this is the equivalent fourth or fifth order method on a much compacter stencil, including the central stencil and all the directional ones. So this is great news for everyone looking to deploy this sort of methods, because first of all, you have a much smaller footprint of your stencils, which is really great for parallel scalability. The second thing is that it is much more robust, because you are combining higher order polynomials with lower order polynomials arising from the smaller directional stencils. And we achieved at least 30% faster computational times compared to the traditional winnow methods that we were using before. So for the past, let's say, 2-3 years that we have developed these methods, I have not looked back, and the rest of the colleagues in the team, they are using these methods more than the traditional winnow types of methods because they are much cheaper. Then we did some work on higher order muscle schemes, and there was quite a lot of discussion about how you're going to increase the order of accuracy for muscle methods, because they are essentially strictly monotone preserving, and they are limited to second order of accuracy. So we did some work on redefining the boundaries in terms of allowable solutions, and we were able to achieve higher order of accuracy without sacrificing the non-oscillatory properties of the methods. So you can see at the top a third order or a fourth, this is a fourth order limiter that was the one by Mittelach-Goose variant. And on the bottom figure, you can see the new limiter indicating the regions where the limiter is actually working. So we managed to have the limiter being activated only across the shocks or regions with really sharp gradients, rather than being triggered falsely by the element types or the grid sizes. So when you have unstructured meshes, the limiter can easily trigger itself because of the difference in terms of element size, element shapes. So this arbitrariness in the mesh can falsely activate the limiters. So this is something that we managed to avoid by redefining the bound. Then we looked at fortifying and making further options available for explicit time stepping and implicit time stepping techniques. Implicit time stepping techniques are necessarily used for very high Reynolds number flows that we have done. And when you want to dictate a time step not on the CFL criterion, but you want to bypass this limitation. So we run typical viscous flow problems for high Reynolds numbers. This is a hypersonic problem that we have tried lately. This is with implicit large edge simulation. This is with RAN's terminus model, and this is a complete aircraft with I think this is with delayed detached simulation. Next, we focused the last I think it is 4 years that we are doing this work with Mood. So it started as a tool that has been put together by Raphael Loubert, Stefan Klan, and who else? Yeah, I think there were a couple of researchers from Bordeaux. So what they did, they designed a decision-making algorithm. So the brain of a posterior a maximum optimal order detection while a simulation is running. And what it does is, while the simulation is running and it's performing center operations, so to do a high order interpolation, extrapolate the gradients and the variables at the Gaussian quadrature points, do some interpolation exchanging, we compute the fluxes. And once we compute the fluxes, we have a candidate solution. So this candidate solution is scrutinized under certain physical admissible detection and numerical admissible detection criteria that, depending on if they satisfy this criteria or not, they can be viewed as a valid solution, or if they don't satisfy them, we have to revert and use a second order method, a first order method, and so on. However, this was the initial implementation.
Sorry. What are the criteria? Like, can you give us a flavor of
Yes,
the criteria?
so initially the physical admissible detection criteria was that you don't end up with solutions that can admit negative energies, negative densities, and so on. So it is more about physical meaningful results. The second numerical admissible detection criteria, it is focused around discrete maximum principles. So looking at the closed boundaries of the considered cell and seeing if the new solution violates certain of the bounds of the surrounding elements. And that was the initial concept. And it was mainly focusing on detecting the maximum order that we can achieve. So I was aiming, let's say, for a fourth order scheme, and at certain regions, it might drop to third, it might drop to second, it might drop to first. So we took these methods and we evolved them furthermore. Let me see if I have it in the next one. No, I didn't have it in the next one. So we evolved it furthermore. And what we did was not only decide about the order of the scheme, but maybe decide about the gradient approximation that we're using, maybe decide about the framework that we're using. So we might be able to switch from finite volume to finite element framework. We might be able to switch and use different dissipation control for our methods by using this technique. However, the main bottleneck and disadvantage of this posteriori technique is that it is posteriori. So bookkeeping is translating with a computational overhead, because you have to compute these candidate solutions and you have to revert back. And this has to take into account that once you have reached this point to compute a candidate solution, if the solution is invalid for some reason, this means that you have already contaminated through the fluxes the neighboring cells that might belong to a different CPU. So it comes at a price. So we are focusing nowadays on using this technique in a priori fashion rather than in a posteriori fashion, because we want to scale it up and use it for implicit time-stepping techniques, which is not that obvious how to implement it for implicit time-stepping techniques in a posteriori fashion. We did recently some work for some really challenging test problems with this mood algorithm, and in particular, shock-induced collapse of bubbles. So these are the test problems that are usually experienced in several studies looking at nuclear fusion. We focused mainly on the hydrodynamic aspect of things. And here you can see the regions where they have been solved with everything, I think, is with fifth order of accuracy. These areas are with, I think they are with second order of accuracy, and there are even regions that drop to first order of accuracy. Because of the very strong gradients, the criteria that we used did not admit valid solutions higher than first order in certain areas. In terms of the models, we started with the linear advection equation. Then we moved on to Euler, non-hydrostatic Euler equations to calibrate our models. We moved on then to turbulence modeling techniques, in particular runs with Spallard-Tallmadge turbulence model and different implementations, and K omega. We moved to delayed detached dissimulation, and of course, under-resolved DNS or ILES, so running simulations without an underlying turbulence model, and direct numerical simulations whenever we had the resources to do this sort of studies. Another work was to further expand the framework to rotating geometries, so flow in rotating rotor blades, wind turbines, and so on. So we did some development of a numerical framework where we use variable multiple reference framework. This is intended for steady state calculations, where the user doesn't have to worry about building a mesh for the rotating component and another mesh for the rest. So this is done on a software level. So the user just defines the MRF region, and we do interpolations in between the variable, the rotating frame and the stationary frame with high order of accuracy across them. It has been used successfully for steady state calculations with runs models, but we're now looking to expand it to unsteady problems, and we have to get rid of the MRF, so we have to use either overset or sliding mesh. We are doing some work with overset meshes lately. Multiphysics modeling, it is quite natural to expand it with finite volume methods, especially if you have good shock capturing mechanisms. We started doing some work with the diffuse interface method, so 5 and 6 equations of Aller and Capilla, enriched with some cavitation models. We published this work lately. Overall, the higher order methods seem to benefit this sort of technique, the diffuse interface method. So the diffusion across the material interfaces is not as pronounced when you use a very high order method. But for the second and third order methods, they can also benefit by using some interface sharpening technique, which is something that we are also working on, because third order methods can also benefit from this interface sharpening algorithms that are out there. Yes, so interface sharpening might still be needed for up to third order methods. So this is from a simulation of a shockwave hitting a water droplet, where the water droplet, we have cavitation taking place inside with all sorts of different structures present. So that was from the National Supercomputing Archer competition that we won a video in 2021. In terms of software, so we have applied the software UCNS3D to different applications in the industries, from automotive, aerospace, defense, climate, health, energy, biomimetics, where we run simulations of formation flying with UAVs. And we have been generously being supported by UKRI, Innovate UK, EPSRC, EU programs that they were focused on making the software to be parallel efficient, being able to run very large meshes. We got supported by HPC Europa and Research England. And it started as a pure Fortran software. It has, nowadays it uses certain libraries. So it is available for free under GPL3 in GitHub. It is using object-oriented Fortran programming. So you have different data types, object types, and so on. We use certain BLAS libraries for matrix multiplications and matrix vector multiplication that was implemented in a European project, HOV1. We did some work on MPI-IO for very large data files, and Parmetis for partitioning very large meshes. That was done with the HOV2 program. And we also expanded OpenMP implementation of the code rather than only MPI at the latest HOV3 EU program. So the great news is that with the latest OpenMP variant, you can also port certain sections of the code to GPUs. In terms of input files, we use the most popular formats like UGrid, star format, and fluent.msh formats. It outputs the solution in TechPlot or VTK formats, binary or ASCII. It runs on Linux, Macintosh, where you can compile the source codes, and it also runs on Windows through the Docker application. In terms of parallelization, again, we can benefit from the higher order of methods because they demonstrate better scalability. You can see here, for instance, that a standard second order method seems to drop by 21.4% scalability, parallel efficiency at 10,000 CPUs, while a sixth order method on the same mesh achieves 72.8% parallel efficiency. Of course, this particular test problem is running at an extreme if you think that we are using just 21 cells per process. But it is a good indication of the situation and the landscape that it is being taking place when you have millions of cores and that you can deploy to run your simulations. So you can easily run in these sort of scenarios. We recently ran a massive simulations for, this is the biggest one that we have run so far, which is on 131,000 CPUs in the HLRS system Hawk with AMD EPYC ROM CPUs. So roughly 33 billion reconstructed degrees of freedom. And we managed to achieve a scalability of close to 80%, running an implicit large edge simulation of an aircraft at landing configuration. So this is using a fourth order method. So it is nice to see that we have started from something really fundamental and we are able to scale it up and run some complicated geometries where you will definitely have some issues in terms of grid quality at certain regions, but your numerical framework and software needs to be able to survive this sort of challenges. The key points for the software is that it is free, that it is open source, so you can further expand its usability. It is documented, so there are a lot of repositories with test problems. There are test cases with documentation on how to run them. It is essentially a research platform for methods, models, and software. I view it more as a research platform where I use it on a daily basis to do some research on certain methods. And of course, we apply it to different sets of problems. So me in particular applied for aerodynamic flows, mainly in the aerospace sector. And a nice desirable aspect about it is that you can run it using as many resources as you wish for free. So it doesn't come with a license to run on as many CPUs as you want. You take as an input something that you can generate from an open source or a commercial grid generator. You run the CFD solver, and then you can post-process it either using some open source or commercial post-processing packages. This is the result of a great team effort. So I'm really honored and privileged to have collaborated with several people and being supported by a great team. So I really enjoy working with them, and everyone is taking pride in feeling ownership of this software. So everyone has contributed, and that has contributed feel that they own the software itself. And this is really something that makes me happy. And in terms of the future, we are looking at three different pillars. So methods development, models development, and software development. In terms of the methods, we have some work that we started on blending finite volume and finite element methods using the mood technique to control the decision making, overset meshes, and higher order implicit time stepping, and some adaptive dissipation control for implicit or classical LES. In terms of the models, we are doing some work for enriching the 5 and 6 equation models with Barnard's Yato 7 equation models, wall model LES with Lin Fu, real gas effects for hypersonics with some colleagues here from Cranfield, and in terms of software, Python interfacing and GPU offloading with OpenMP. So this is part of some work that we have done lately. It is still under review, but we have done some hybridization of DG and finite volume. What is unique about our approach is that we are not only, well, we start with a DG framework. So we're using the code and we solve the model DG implementation. The DG solution is scrutinized in a priori fashion. And if the solution does not satisfy certain criteria, then we switch to a high order finite volume solution. But we also scrutinize the high order finite volume solution because it might still contain some inadmissible solutions, or it might still contain some oscillations that might make the whole simulations blow up. So we looked at different troubled cell indicators. We looked at when to implement them, how often to call upon them. So we have done a comprehensive study on that. We can see this picture that we have run this test problem in particular that we have tried in the past with a pure finite volume method. And we can see the regions that the finite volume gets activated. But we are really lucky because when your other alternative to a DG solution is a high order finite volume solution, you can be really fortunate in the sense that the way that you design your troubled cell indicator might not be that important, because even if you switch to a higher order from a high order DG solution to a high order finite volume solution, you don't lose that much of information. On the other hand, if you were switching to a massless second order method or a TVB or a TVD kind of limiter, then the design of the troubled cell indicator becomes more and more important. And of course, the troubled cell indicator is directly linked to the computational overhead. So it is important just from the computational aspect of things rather than losing accuracy by switching too frequently to a higher defined volume. So the hybridization benefits both frameworks. So we have increased robustness in the DG framework because you can always get away with a finite volume solution, because at certain regions the grid quality might not be that good. It might trigger all sort of bad things happening in the DG framework, or you might have certain phenomena, certain oscillations in the solution. So we greatly benefit from hybridizing both of them. And it was quite natural to do in this framework because we're using already Gaussian quadrature rules, we're using polynomial basis functions, and it was quite natural to bring DG within the framework.
I have a question. I have
yes.
a question on this.
Yes.
If we stay with DG,
yes,
I work on DG in 1994 for first time.
No, right now.
Yeah, but let's say DG, and you're right, it's very sensitive. But I was wondering, and one of my students long time ago, 20 years ago, did the super collocation. So in other words,
yes.
Which will mimic what you do with the least squares in finite volume. Would that super collocation give you the robustness that you want so that you can pass the criteria? Have you actually checked that? You guys have checked that?
Yes, we have tried filtering. We have tried over integration.
Yes.
Not always, at least in the type of cases that we are looking at, because as I said before, we need to be able to run a simulation on meshes that they are not that good. So we see that the finite volume is not that sensitive on grid quality. So at the beginning of the simulation, there are certain regions that might dictate that the finite volume stays for that cell for the entire duration of the simulation because the grid quality is bad and you have aliasing errors or all sorts of different things. We still have issues with filtering. So
yeah, no, filtering, I agree, but the super collocation, yes. I was wondering, like, over integration.
No, we haven't tried the super collocation to be honest. So this is something that
over integration. It's Mike Kirby's thesis, and then I think Spencer Sherwin also is using it now, and other people are using it. Yeah.
Yes, or
it would be interesting, an interesting paper to compare exactly what you have here, which I agree with you. You know, it's the robustness of finite volume is it's certainly a great attribute. But to see if you can if the over integration could account for that robustness to endow DG with some robustness, right? So it would be like interesting comparison, actually. Yeah.
Yes. I totally agree. And so we run into aliasing errors. So we run the under-resolved subsonic Taylor-Green vortex. And initially the results look good without doing any filtering of the solution. Especially we get really good agreement with Kolmogorov slope for dissipation rates and so on. But you can say that the solution is quite noisy. So this is down to aliasing. But because we're using model DG, we haven't managed to run in a simulation where we can use P3, P4, P5, and the simulation will crash. It will keep on running, but it will just be noisy. So we're doing some work on filtering, but adaptive filtering. So not filtering everything, filtering selective cells based on some criteria like energy ratios and things of this kind, which is some of the work that I have done with a couple of colleagues. And it is part of a late work by Andrea Beck and Moons. So they're doing some filtering, but selective filtering on certain cells under certain criteria. And this is part of the work of adaptively tuned high-order unstructured finite volume methods for turbulent flows. So we are using the previous algorithm, the MOOD, but in a different fashion now. So we are looking at controlling the dissipation and dispersion of the numerical methods to ensure that we get physically meaningful results and the dissipation that is correct in both finite volume and the G framework. So
I have a question here. Sorry.
Yes.
I have a question. How do you calculate the correct dissipation?
The correct dissipation. Okay.
Like so
yes. So what the simulation is running for locally for every cell, we look at the energy ratio. So we have the candidate solution, which is the unfiltered solution that might be coming from the DG or the finite volume framework. So this is one. And then we have two other solutions that are solutions obtained through filtering, a very strong filter and a weaker filter. And we measure a couple of things. So we measure if there is high frequency content in the solution for that particular cell in terms of kinetic energy due to being under-resolved, which implies that we need to do certain things regarding the dissipation or the dispersion of the numerical method. The second thing is we might have some high frequency content because we might have some strong gradients and we might have some high frequency content. So we usually select to scrutinize the regions where the Wino limiter is not really active. So in cases where, so the window limiter gets activated, then might dictate that we need to reduce the, let's say, order of accuracy because I have sharp gradients and I'm using certain stencils. Now, for the rest of the domain that we have smooth flow structures, these are the ones that are scrutinized mostly to ensure that we introduce the right amount of dissipation to resolve certain things. So this is a work that I have done and I have published at, I think it is JCP with Jesus and a couple of other colleagues in energy ratio being used in the finite volume framework and for structured grids. And we are taking this concept and extending it to unstructured grids and DG framework as well. So yeah, at the moment, we are still doing calibration for the DG and the finite volume in UCNS3D with this decision-making mechanism. But so far, we are still here. So we are using it in a priori fashion. We haven't looked at posteriori because it is much more complicated. And yeah, we will look at that in this next year through this project that we got. Yes, so this is the kind of developments that we are doing. So thank you very much for your time, and I'm looking forward for any questions that you might have.
So I have another question. This is Ahmed from Brown. So
yes,
have you compared your code in terms of parallel efficiency against like other discontinuous spectral element code like Nectar++ or PyFR?
I haven't compared against I mean heads-to-heads comparison, but we have done benchmarking in the previous national facility here in the UK called Archer that had something like 120,000 CPUs. So that exercise was actually to inform the procurement of the next system, which was Archer 2. But we have been able to scale up to, let's say, 200,000 CPUs, a relatively coarse message. So I'm pretty sure that scalability is not an issue for certain methods. So I'm talking purely for implicit large eddy simulation techniques. If we're talking about runs, delayed detached eddy simulations, and so on, these do not scale that well because they are inherently implicit. So you have all sort of collective communications taking place. So these do not scale that well. But we have done comparisons against commercial software like Fluent and Dance's CFX for run simulations, and we are quite close in terms of the performance that they achieve and we achieve with the default settings without doing any, let's say, tuning in terms of selecting the right settings for ours and selecting the right settings for them. But yeah, depending on the method, so implicit large eddy simulations and large high order methods, they scale really, really well.
I have another question if I can ask another one. So it's about the multi-species flows, like when you have material interface. So how do you handle those numerical oscillations induced by material interface? I know there are some methods in literature like double flux method that you sacrifice some conservation to remove those oscillations.
Yes. Yeah, with the diffuse interface method, you're running in a much more robust framework because you don't use a front tracking algorithm or stuff like that that does not allow, for example, bubbles to collapse on themselves and things of this kind. But across the material interface, you will get oscillations unless your underlying shock capturing method, finite volume limiter, or WIN, or whatever you are using, is not robust enough. So we are making sure that when we run the multi-physics problems, that we run with different settings for the C-WINO or the WINO methods, mainly the C-WINO. These are the ones, the compact ones that we're using. So they have much more tight tolerances, so they don't allow any oscillations at all. And this increases the robustness significantly, because if you allow any oscillation, and we are talking about really violent phenomena that we are exploring there, they have the potential to blow up the solution immediately. So you have to ensure that you use certain thresholds that do not allow for any oscillations across the interface. So this is what we are doing.
Thank you.
Yeah. Hey, hi, I'm Raj. I have a question. I'm from Brown. So you mentioned on slide 15 that you also handle the adaptive mesh refinement.
Yes.
So is it based on the local error estimate, or you use some sort of tree structure to do that? Like, how do you, like, could you please comment on how do you do this adaptive mesh refinement?
Yes, we did some adaptive mesh refinement studies, I think, for 2 years, but we were not so happy with the results, to be honest, because we were limited to conforming mesh refinement, and we realized we have to go into non-conforming mesh refinement to get significant benefits. So we used the local error estimator. So we looked at well, we used at some point the smoothness, the oscillation indicators that we're using for the WINO methods. So we looked at certain, let's say, variables, mainly density or pressure, for refining the mesh at certain regions. Yeah, this is what we use. We use the same smoothness indicators as the WINO methods.
Okay. And how is this performance across the machines? Like when we port this code from one machine to another, so would it hurt the performance? Like, or we need to refactor some of the part and then?
No. You will get a good performance out of the box, and good scalability for certain techniques. So you are not expected to scale that well for us. This is for sure. So when I'm saying that you are not expected to scale well for runs, I mean that you might be able to run a mesh of, let's say, 50 million elements within 1,000 cores and still get really good performance, but it will not go to 100,000 or 200,000. You can run it, but you will not get the parallel efficiency that you will be aiming for, because inherently these methods, for the implicit methods for runs and so on, they don't scale that well.
Okay, thank you.
But if you use an explicit time stepping, it will scale really well.
Okay, thank you very much. Thanks.
Yes.
Tax, you talked about hypersonics in the beginning, but I don't. You actually have hypersonics with a real chemistry and dissociation, real chemistry in the code.
No, real chemistry not yet. So there is a PhD student starting with me this fall that is going to work on chemistry, real gas effects, and so on. So we have done work with runs, delayed detached dissimulations, and implicit layered dissimulation on hypersonics. So lately I'm doing some implicit layered dissimulation work on hypersonics, but not yet with the real gas effects. This is something that...
but you do have the dissociation of the gas, right? You have three or 5... Oh, you don't have a dissociation?
No, nothing yet.
Ah, okay. I would not call that hypersonics.
Yeah. So we are running at Mach 5. So
okay, that's
the
marginal.
limit, let's say.
Yeah, the limit, that's the limit, yeah.
Yes.
Also, I have a question. This is a very ambitious project. It's like, congratulations.
Yes, thank you.
Where do you find all these people who know Fortran? to the
Well,
I don't know any people here who still know Fortran.
Yeah,
I do, but I don't
yeah,
know any. Maybe Raj
yes,
knows Fortran and Ahmad, but not other people. I cannot find
yes,
any people who know Fortran anymore.
yes. This is true, George. And interestingly enough, there was an article or a study that came out. I think it was a week ago, where almost 75% of the codes that are being run on the national HPC facility here in the UK is Fortran codes. So the question is, who's running them? So I think there is still, yeah.
Some Mohicans.
Yeah. So I think it is, if you know one programming language, I think it is easy to get on board with Fortran, or if you know Fortran, to get on to C or C++, and the other way around. Python is a different beast on its own because it has a completely different philosophy. But yeah, if you need to have a really good, let's say, how should I say, productivity in terms of easily transforming a mathematical expression into a code, I think Fortran is quite natural. To me, it seems quite natural. So that's why we.
I think Ahmad, you have a comment. You raise your hand.
No, I was just happy when I heard 70% of the simulation is done by Fortran in Europe.
In England. In
England. Yes.
Not here.
It was interesting.
Yes.
Raj, do you want to say something about Trixie and Julia and so on? So Panos can get some
yes.
Yeah, so that's why that's why I asked the first question. Like, so there is a package called Trixie Julia. So
yes, I have heard about it.
So their adaptive mesh refinement, like although that was developed by one of the alumni from the Brown, like Lucas Wilcox, so they use octree-based method. So you don't need to you don't have to follow the local error estimate. So they just divide, and although there is a problem with some hanging nodes there, so that is the one aspect. And it's not just refinement; it coarsens back also. Like if suppose your shock wave has passed, and you don't need that much refinement. And so that's this is pretty much on the Julia interface. So there is no like interpreted language overhead or something like Python or Python has. So it's very scalable. So I tried few solvers there, and it was scaling very well. I had access to 1500 code, so it scaled very well. So just to free. And second thing was that I was recently in the talk by a scientist from Argonne, and he was discussing about performance portability. So there is a one thing, like I'm not sure if it is available in Fortran, but in C++ 17, you can directly offload the code to GPU without coding in CUDA.
You can do it, and this was the great development of OpenMP. So you can also do it in this code. So this code has OpenMP directives throughout because it is not a pure MPI code. It is MPI and OpenMP. So it has directives, parallel regions, and so on. And within these parallel regions, you can port certain things with OpenMP without using CUDA. And this is one of the great developments of OpenMP, is that you can port sections of the code that take quite a lot of time to GPUs that without using a vendor-specific, programming language. So you can port it to Intel, AMD, NVIDIA, all of them. So this is a part of the work that a PhD student is going to look at.
And there is another interface called Cocos. So I'm not sure if it is applicable for Fortran, but for C++, it is very well developed. So that's also like you don't have to write any CUDA specific context and all those. And performance is not hurt because they were struggling. Like most of the old code are like not like giving same performance on the new machine. So that like Polaris, Aurora, and those machines. So that was just some comments on that. So that's but very good talk, and it's really tempting to try this solver. So
yeah, thank you.
Is there any other question for our speaker? Okay, thank you for your.
Okay, thank you so much, everyone.
George, do you want to say anything before we?
No, just to thank the speakers. Thank Takis from giving this talk. We most of our talks are all our talks are machine learning, but I thought it would be nice to. We're sort of slowly getting back into codes, high order codes for hypersonics with real chemistry, and so Ahmad and Raj that talked here are developing 2 different versions, collocation and Galerkin type codes with real chemistry and 2D and 3D. But we're very impressed with Trixie, especially the refinement and de-refinement. De-refinement is always very difficult, as you know.
Yes.
And the refinement, so that is, but it doesn't have, and we're now working with a developer. Some of the developers are in Germany, and another one is Jesse Chen in Rice, who was the advisor of Raj, who just spoke. So we are trying to, because the problem is we survey the field and there's no high order hypersonic codes, real chemistry and so on. So that's there's a real need for it right now. And some people are misleading in their advertisement. For example, they say they call the high order because they have a second order Riemann solver. But everything else is first order. So for hypersonics, for which we don't have the experimental, lots of experimental data, it's very dangerous to run with low order. So keep us posted on what you're doing on that front. When you
of course. Thank you very much, George, for the kind invitation. So
Okay, take care, everyone. Bye bye.
Okay, take care. Have a lovely weekend. Bye.
Bye. See you guys.
Bye.